Hello, everyone, and welcome to today's webinar, Development of the Next Generation Water Resources Modeling Framework. In just a moment, we'll be hearing from a number of folks at the NOAA National Weather Service Office of Water Prediction about the Next Generation Water Resources Modeling Framework. But first, a few notes and logistics. My name is Julia Masterman. I'm the Science Education and Outreach Coordinator for QUASI. QUASI is the consortium of universities for the advancement of hydrologic science. And our mission is to advance water science by strengthening interdisciplinary collaboration, providing critical infrastructure through our data services, and promoting education in water science at all levels. Visit our website, sign up for our newsletter, join our community Slack channel, or follow us at QUASI on Twitter to learn more about what we do or to get involved. I'll add information on all these things to the chat in just a moment, as well as the National Water Center's Twitter handle. But first, a few things to note. The webinar is being recorded and will be posted on the QUASI YouTube channel later this afternoon. Please ask any questions you might have via the Q&A feature in Zoom or in the chat. And our presenters will do their best to get to as many as possible. I would encourage you to use the Q&A feature if possible, though. Thank you again for joining us today for the webinar, Development of the Next Generation Water Resources Modeling Framework. And with that, I'd like to introduce Fred Ogden, scientist at NOAA National Weather Service Office of Water Predictions.
Thanks, Julia. Can you hear me okay?
Yep.
All right, let me share my screen.
So Julia, I want to check and make sure that you can hear and see me.
Yep.
Okay. Well, hopefully Fred's internet access trouble is only temporary. So for those of you who don't know me, my name is Trey. I'm the Director of the Analysis and Prediction Division at the National Water Center in Tuscaloosa, Alabama. And we are the ones who are responsible for developing the National Water Model. So Fred recently joined us as our Chief Scientist for the Office of Water Prediction. And we're incredibly happy that he has been leading the charge here on the effort to evolve the National Water Model to the next generation. We've been operating the National Water Model on our weather and climate operational supercomputing system. We've been operating it for the last 5 years. And the version 1 of the model went into operations in August of 2016. And since then, we have learned a lot about that system, how to develop it, what our greatest development challenges are, and how to accelerate the improvements in the forecasting skill we're able to realize out of the system. As I said, Fred has been leading the charge. He's been the leading voice in the technical side of that, and it looks like he has rejoined. And so, Fred, I want to do a quick sound check with you. Make sure you are indeed back with us.
Testing 1, 2.
We have you 5 by 5, Fred. The floor has been returned to you.
Thanks. Sorry about the hiccup there. I had nothing to do with any of it. Let me start talking about, first with a little bit about the National Water Center. Many of you are aware the Water Center was created by the National Weather Service to serve as a focal point for water prediction within NOAA, National Weather Service. And just in the last year, Congress passed Public Law 116-271 that says that the National Water Service functions to serve as the research and operational center of excellence for hydrologic analysis, forecasting, and related decision support services within the National Oceanic and Atmospheric Administration and National Weather Service. It's also got a codified function to facilitate collaborations across federal and state government departments and agencies, academia, and the private sector on matters related to water resources. And it's nice to have that codified. The authority that's given to the National Water Center include improving understanding in water resources, stakeholder needs regarding water resources, and identifying science and services gaps related to water resources. Develop and implement advanced water resources modeling capabilities, facilitate the transition of hydrologic research into operations, deliver forecasts, analyses, forecasts, and inundation information for the guidance of hydrologic events in the United States, including flash flooding, riverine flooding, and water resource outlooks. And then in coordination with warning coordination meteorologists, the folks out in the field that issue flood warnings, for instance, we are to provide decision support services to inform emergency management and water resources decisions. So that's the range of activities that are authorized at the Water Center. The National Water Center is operated by the Office of Water Prediction within National Weather Service, and there's the vision and mission statements. The photo shows a photo taken inside the rotunda for those of you who haven't been there. We host a lot of events. I believe that to date we've had about 3,000 participants attend events at the National Water Center. It's a very nice facility with a very open design and layout with a lot of, I would say, collaborative spaces as well as instructional facilities included. And I just wanted to announce that we do have a sabbatical opportunity at the Water Center for somebody who's interested in working with us about some of the ideas that I'm presenting today. If you're interested, there's my email, and I'll show this again at the end of the presentation. So the National Water Model was originally proposed in 2011 by Quasi. It was proposed as a community model. There was a lot of interest in the academic and research communities. In fact, I was on the board of directors of Quasi at that time. But ultimately, it lacked agency support because the agencies have all developed their own systems and frameworks and have their own models, and they weren't looking for another one at the time. In 2014, the National Weather Service recognized the potential for predictions outside of traditional forecast points, which is what has been and continues to be done by the river forecast centers. And in 2016, National Water Model version 1.0 was operationalized by the Weather Service, and it was based on the WRF Hydro framework, which is NOAA-NWS plus routing functions and a conceptual groundwater component. The National Water Model is a great enhancement to the capabilities of the Weather Service. These blue lines show the streams where forecasts are issued by the current operational Weather Service models. It's approximately 110,000 river miles. The National Water Model enables forecasts on 3.4 million river miles of stream. So a many order of magnitude increase of resolution and the ability to make predictions. The current operational National Water Model version 2.0 formulation consists of these components. It uses NOAA-NWS running on a 1 kilometer grid in a particular configuration to do the energy balance partitioning and rainfall flux partitioning at the land surface. Excess rainfall is routed on a 250 meter grid using a simplified version of the routing diffusive wave routing scheme. Lateral subsurface flow is routed on the same 250 meter grid using a Busan-esque type approximation. Base flow is simulated by a conceptual nonlinear reservoir. That water is routed in a vector-based Muskingum-Coons channel routing methodology. And we have added basic water management incorporating release data from reservoirs where available. And so that's the current operational configuration. If we have analyzed that performance of the model at the event time scale, this figure shows the percent error in peak discharge this is at the 50th percentile. So this is the median error in peak discharge at the event time scale. we see that there's a significant regional variation in the performance. The larger dots are better. They are plus or minus 25% in the median sense. The smaller dots are errors greater than plus or minus 25%. You can see that there are areas of improved performance on the windward side of the Appalachians and in the Pacific Northwest, in some Rockies. This is warm season only. We tried to avoid snowmelt and cold regions processes in these analysis. And in the Midwest, you'll see that model performance is not so good on, say, the coastal plain, mid-Atlantic area, the Southwest, the High Plains regions, parts of Texas. There's a significant variation in the regional performance of the National Water Model. And if you look at that, this top plot shows the annual runoff ratio from using data from USGS reference gauges where mean annual precip is provided. There's a tendency towards the National Water Model in its current operational formulation to perform better in places that are wetter. That isn't generally true, but there is a decent coincidence. So you could say that the formulation might be more suited for wetter areas. And part of that is the role of groundwater. This plot shows the aridity index, and you can see the striking contrast between the eastern half of the country roughly and the Northwest versus the rest of the country, where there's just a lot less runoff produced for the amount of rainfall that falls in a given year. Now let's talk about predictability processes and parameters. Why would we expect to see a model applied pretty much as a uniform formulation across CONUS struggle regionally? So I'll kind of step through these figures. This is a figure, I've showed this at AGU, and I like it because it's based on my experience and understanding of the processes. There's really no hardcore data points behind it. It's really more of a conceptual figure. Over on the left, the dominant parameter there for infiltration excess is the ratio of the rain rate to the potential infiltration rate. Over on the right, at the other end of this spectrum of runoff generation processes, is what I'm calling P over S, the storm total precip relative to the total catchment storage. And the time that storm total precip is integrated over can vary and does vary. Over on the left-hand side, we're in the land surface dominated regime, such as is common to see in arid, semi-arid climates, where you have dust sealing or just general low soil permeability that might be associated with fine and disturbed soils. And that would include tilled agricultural lands. And it's typically deep to groundwater. On the right-hand side, we're in the groundwater dominated regime. That's a photo I took when I was living in Connecticut of a small catchment where we had done a lot of studies. You never saw surface runoff there. The groundwater table is at the same elevation as the stream elevation, and there are very little fine grained textures in the regolith, if you will, because it's not really what I would call soil. If you look out there on the land surface, it's mostly cobbles, boulders, gravels, and some sand. But in both of those cases, in the land surface dominated, and I'll go back one slide here, we can model parking lots all day with a pretty simple model. We have high predictability and a small number of parameters. And it's very sensitive to the rain rate. If we have a big error in rain rate, we're probably not going to make a very good prediction. On the right-hand side, we need to know how much rain, what's the antecedent moisture condition. It's very sensitive to the water balance because that determines where the groundwater table is going to intersect with the land surface. Typical of humid climates with coarse soils and shallow bedrock. Now in the middle, there's this vast parameter space, and I've denoted that with this spectral symbol bar down at the bottom, where there's a lot going on, and I will call that soil-dominated hydrology, where layering is important, seasonality is important, and that would include freeze-thaw processes. Macropores can be dominant, heterogeneities matter a lot. Behavior thresholds arise, Anthropogenic effects are important, and it creates a lot of transient phenomena. And we just, in that area, generally lack a comprehensive theory of stormflow generation, because the land surface we can observe, the groundwater system tends to be a little bit less dynamic and more amenable to parameter estimation. In the soil dominated regime, a lot of stuff matters. To know it would be to destroy it. It's a really challenging problem. And then this is just a good example of that. This is Iowa after an April thunderstorm, and I'll zoom in on that. It's the same rainfall, the same soil, the same land use, the same slope, the same aspect. We would apply the same model on both sides of that fence, and one of them would definitely be wrong. And it's because of the tillage practice, how the farmer manages their land. So this creates a wicked problem. A wicked problem, if you look at the, probably one definition is, a wicked problem is a problem that when you ask a question, the answer is it depends. And in hydrology, almost every question that you ask, what causes runoff to occur here? You could say, well, it depends. It depends on the season, etc. It depends on how the farmer tills their ground. It depends on whether there's fine textured material or whether it's impervious. There are lots of those. What it implies is that there's really no one model to rule them all. So here's an example comparing a distributed physics-based finite difference groundwater model in a shallow aquifer system to predict saturation excess runoff versus a conceptual topographic wetness index model, top model. And if you look at the top left figure, it shows that in terms of hydrologic response, and we simulated a small catchment in this example, there's a lot of similarity. But when you look at a plot of the fraction of the catchment that's saturated versus soil moisture deficit, comparing the finite difference scheme versus top model, there are big differences. The top model concept makes some assumptions that prevent that model, and actually it wasn't intended to predict that function correctly. The dynamics of the groundwater table are what determine that, and top model does not explicitly simulate those. So the hydrograph compares very well. Top model doesn't simulate the moisture dynamics correctly, but for predicting flow, is that important? And this is an example where using a simplified model can give you very similar results in terms of the hydrology response and save a lot of CPU cycles. And there are many examples like that. Now, in the next gen framework, Weather Service has been operating the water model since 2016, and we're finding that version on version, the calibration results in an incremental improvement in performance. It seems as though we're bumping up against the limits of the formulation in the context of the predictability problem. And we originally thought that we might modularize and modernize the water model code, but it's written in an older dialect of Fortran. The subroutines are many. The coupling between them is pretty intensive. It takes a lot of time to think about stripping a component out of the current national water model and making it a standalone module, which gave rise to the notion of a next-gen water resources modeling framework. Now, the next-gen national water model will be a particular implementation of that framework. In terms of the enabling technologies, a lot has changed since National Water Model was proposed by Quasi back in 2011. We've had some significant advances in computer science and engineering with GitHub and the development of the BMI model coupling interface. We've had recent big advances in data science standards for geosciences, including WaterML 2.0 high features data model and other ways of dealing and handling large data sets. And in terms of hydrologic science and engineering, if you look at the literature, there are there's definitely, because of the wicked nature of the hydrology prediction problem, there are a large number of models out there that have been demonstrated to have superior skills in particular situations. And I am not advocating any particular model. What I'm advocating is that we develop a framework that will allow a scientific evaluation of different formulations. So the little cartoon there just shows some of them. And I think the heavy hitter on this list might ultimately turn out to be the machine learning approach. But we won't know until we can test that. So regional variation in performance suggests regional formulations might be important for the national water model. The parsimony argument, which is another version of Occam's razor, optimizing complexity is likely to speed simulation with increased predictive skill. The WaterML 2.0 high features data model will allow model setup, workflow unification. Right now, almost every model that exists has its own data model. This will get us out of that way of thinking if we can agree on a data model. And that will give us a consistent method to couple models to a hydrofabric. And a hydrofabric, I'm talking about that in the context of the definition of catchments, flow paths or streams, water bodies, and the things that connect them. And in terms of computer science, open source development, using the existing BMI standard for coupling, Moore's law isn't going to save us, so we're going to have to be smart about how we use our computational resources. And machine learning is poised to make significant advances as well. This is just a simple schematic showing the WaterML 2.0 high features data model. And this was work Dave Bludgett from the USGS participated in this. Catchment definition. A particular model formulation can be used at a catchment. They don't have to all be the same. Where a flow path is a 1D type of feature that moves water, could be simulated using Muskingum-Kunz or hydrodynamic routing, however you wanted to get that water from one place to another. And nexi or nexuses join catchments to flow paths. And then down towards the outlet of this region, we've got a water body that could be a reservoir. It's a 2D object or maybe a 3D object that exists in the model domain. And it would be simulated using an appropriate model as well. And it could have rules that go with it or a data ingest source. Now, we had a meeting, a joint interagency meeting between NOAA, Army Corps of Engineers, Engineer Research and Development Center, the USGS, and the US Bureau of Reclamation to talk about requirements for this framework. Each one of our agencies are struggling with model interoperability, and this framework offers a way to get models to play together that have never played together before. The requirements we came up with include model agnostic with maximum flexibility. So as models, data sources, and needs change, the framework can evolve. A common architecture to avoid duplication and promote interoperability. An open source development environment to promote code reuse and development efficiency. It will allow us to create an authoritative repository of federal water models that are compatible with this framework, and ease and encourage participation by partners in the research community. And we'd like to apply standards where available for coding and coupling, data and metadata, model verification, validation, and test data. And we want it to be friendly to domain scientists and engineers. To continue, we committed to sharing models, data, and results by creating a library of model codes and data sets and evaluation tools that can be used to evaluate their outputs. We agreed to establish and maintain a glossary to define terms to communicate clearly across disciplinary boundaries because of the breadth of not only, you look amongst the agencies and the breadth of what they do, but then you add the academic and research communities, it becomes vast. Think about AGU. You can walk across to the next aisle and have trouble talking with someone. We want to use mature open source libraries. We aim to provide multi-language support within the framework. So if your model's written in C or Fortran or Python or C++, if you add the BMI extensions, it should function within the framework. We'd like the framework to run on hardware from laptops to supercomputers, and that's doable these days, not a big challenge. And then this last bullet I think is really important. We've specified we'd like to aim for a 2-week target to allow graduate students or new employees to add functionality to the framework. That will require excellent documentation and step-by-step examples and tutorials, as well as programming. But we don't want to require a computer science background. We want people who are skilled at programming, but not necessarily computer scientists to work. Now, the framework is being written by computer scientists, and it's being written by computer scientists for computer scientists. So if somebody wants to go in and modify the framework code, that the bar will be, it will be rigorous. But it's all being done in a GitHub environment so that there's ample opportunities for transparency and people to participate, etc. So in terms of model coupling strategies, this is the traditional BMI coupling that I think many people are familiar with. But we've pondered, Scott Peckham's actually working with us on this project, and we've pondered adding 2 functions, one to create a serialized running state and one to unpack a serialized running state. And what that will do, the BMI standard was not developed for supercomputer use. By enabling checkpointing, essentially, of a running model, we will be able to run models in an HPC environment and move them around on the machine to balance the load and try to maximize the efficiency of the code. So in addition to all the traditional BMI functions like initialize, update, finalize, etc., we'll have these new functions. And I'll just go back and add, if your model's in Python, you could probably use Pickle or something like that to do this. It'd be a much more straightforward process. The other thing that we're considering is a task-based coupling. And this is something that we've discussed with DOE about. They've noted that in particularly more complex, high-resolution formulations, it's important to not rely on whole model formulations, but to have a library of integrators, solvers, and flux calculators that you can assemble and call as needed. And what that does, it gives the simulation manager the ability to manage all the memory for every part of the model, which is, as you go to bigger and bigger problems, it becomes more important. So this is another development paradigm that we are designing at this point. We haven't started. We have started just recently in the BMI coupling. The problem with task-based modeling is if your model is a simple model like the one on the left, that's high mod, 5 parameters. It's got a Nash cascade and a slow flow linear reservoir and a simple storage distribution function for partitioning a rainfall. It's pretty easy to emulate that formulation using a set of pretty simple instructions. But when you go to a fully distributed process-based model with all of these stores and fluxes you see on the right, it becomes a bigger challenge. And that, I think, is a really interesting research question. How could you tell a computer to emulate that in a distributed sense when it can't be a simple script because of all of the conditionals? If you do this unless something else, some other condition exists, it creates a really interesting question of how you would actually construct a model emulator from component task modules. Different formulations all have different discretizations. They're all valid. Some of them are great in certain situations. Some of them are not valid in certain situations. The upper left would show a cartoon of a real watershed with varied land use, water bodies, streams, soils, maybe some urbanization. There's lots of ways you could approach that modeling. And because no one model rules them all, we can't say a priori which one's going to work best. We can just try some and see how well they work in an operational context. Now, one of the things that we're trying is a conceptual functional equivalent to the current operational national water model. It's 90% the same. The only thing we did was we replaced the 250-meter routing grids for the overland flow and lateral subsurface flow with more conceptual routing elements. But the behavior that we see from that is very similar. It uses this curve number like partitioning function from Shockey et al., which is very similar to Moore, which is actually very similar to the curve number from Marcus. It uses a lot of the same thresholds that are in the National Water Model, and it uses exactly the same deep subsurface aquifer system. Julie, I can't see my clock. How am I doing on time?
Doing pretty well. It's currently 1:30.
All right, thanks. Okay, this is kind of the last lap here. The 2021 Next Gen Development objectives that the Office of Water Prediction has established are to extend the BMIs needed to function in the HPC environment. We plan by AGU fall meeting to demonstrate the Next Gen framework running the conceptual functional equivalent to the National Water Model CONUS-wide. We probably will have top model running in the framework by that time, and perhaps several other models, including a machine learning approach. And it will be linked to the inland hydraulics routing with reservoirs. So the current reservoir modules that will be deployed in Water Model 2.1, which will be coming online very soon, are part of that. And it will be linked to the National Water Model forcing engine. We plan to implement this topographic wetness index model formulation. We plan to develop and implement an infiltration excess model formulation. There's a number of those out there that we'll probably be borrowing bits and pieces from. Improve snowmelt and other flux calculations. So the Next Gen framework, by becoming model agnostic and using the BMI interface, enables plug and play testing of different snowmelt modules, for instance. And that should not only provide a significant benefit to Weather Service in our prediction mission, but also for hypothesis testing and model evaluation by the research community. We want to engage the River Forecast Centers, our other federal partners in academia, and begin calibration and testing of regional formulations in next calendar year, in collaboration with our River Forecast Centers and others. So to wrap it up, the Next Generation Water Resources Modeling Framework is being developed to engage federal and academic research communities using open source standards-based development. It's model agnostic with a focus on interoperability. It will link with NOAA and other weather and climate models. Ease scientific evaluation of coupled models and methods. And then that's really an important point, because it will allow, instead of assuming that one model is good enough, it will allow us to actually compare different models and identify those that outperform others. Running on hardware from laptops to supercomputers, domain science and engineer friendly model coupling interface, with our target of 2 weeks for a domain science or engineering graduate student or a new employee to add functionality to the framework. So the stage is set for this. We're working on it now. We're working with these partners. We are using open source code development, and I'll give you the link to the repo if you want to look at what we're doing. We're using standard geospatial data models and libraries. We're using the CSDMS basic model interface and extending it to HPC. And it will really hit an agency need to promote science and interoperability. So again, we have a sabbatical opportunity if somebody's looking for, and because of COVID and our posture, you know, we're not working in the office, I'm at home. It would probably be a virtual sabbatical, but there's an opportunity for someone who's interested in helping to work on this. And if you are, please contact me at that email. And here is our GitHub site. It's all of our code, all of our developments, all of our documentation, everything's there. And with that, I will open it up for questions. And sorry for the hiccups at the beginning. Are there any questions in the chat?
Hey, Fred.
Yes.
We do have a few questions in the chat and in the Q&A.
Okay.
So the first one in the Q&A is from Jose Molina. Is there a source of the great graph of the relation predictability process parameters? That's I presented that at AGU in December. It's a fiction, it's a piece, it came right out of my imagination based on my experience, my understanding of the literature. All right, thank you for the answer to that. Something similar related to the slides. Daniel Luna asked in the chat, will we be able to get the recording or the slides? And then some kudos, thanks, love the presentation. Yeah,
it's recorded. It should be on Quasi's website, right, Julia?
Yes, it will be posted on the Quasi YouTube channel later today.
All right, thank you, Julia and Fred. We also have another question in the Q&A from George Hsu. Any specific plan about coastal coupling and compound flooding? Is asking because there were 31 named tropical storms in 2020.
Trey, you should answer that question.
I'm more than happy to. Yes, there are definitive plans for coastal coupling and compound flooding. We are in version 3.0 of the model, which will be released in 2023. We will have the first total water or compound flooding forecasting system deployed into operations. We'll be wrapping up that initial development for version 3 later this winter, and the team that is doing that will switch gears very rapidly to develop the first total water forecasting capability in NextGen. We're gonna adapt that to NextGen beginning this next winter. So thank you for that question, George. We have another one. Will it have real-time data assimilation? In other words, of soil moisture in the soil-dominated wicked part of the forecasting area?
So
that's from Michael.
Thanks for the question, Michael. So the framework itself is model agnostic. If you have a data assimilation approach that you would like to test and you want to test it in the framework, you would select a formulation or adapt a formulation to be BMI compliant and plug it in, and then use your data assimilation method on that. Because the framework, when it's run operationally by NOAA, I envision it'll be a very specialized configuration. The more general configuration for research development, testing, and evaluation will allow users in the research community to use it in ways that we don't even want to. The only way we want to anticipate them is to prevent making a decision now that prevents you from doing that in the future. So we're really trying to develop a framework with maximum flexibility, so you should be able to test those. Same thing for the question from Ms. Senbet Sabat. If you have a model that you want to test in a particular region, the framework will allow you to test that model. So the framework is model agnostic. I would say it's also hydrogeoclimatic region agnostic, as long as you can provide forcing data in a format that the framework understands. And I see the question by Felipe. thinks, can you extend a little more on the challenge of implementing BMI on HPC systems? Yes. So BMI was not developed for HPC systems. It was developed for desktops. The challenge is, it's very common. Say if you're thinking about a large scale model, there'll be large parts of the domain where maybe it's not raining or the snow's not melting, and there's just the computations go by very quickly. But there are parts of the domain, and this varies, where there's a lot going on and it becomes very computationally intensive. At runtime, you'll put formulations running on different parts of the machine. And you'll find as you go through the forcing data that the parts of the machine slow down because they're busy. And it's really useful to be able to move models from one node on the HPC system to another. HPC BMI did not envision that. So we're extending it to allow that. We would be able to send a command to a model to say, save your running serialized state and stop running. And then I'm going to, the framework would move that to a part of the machine where there's excess computational power, and then tell it to restart, keep going. And that's done periodically. It's not done continuously, but that's what we mean by extending BMI to do that.
Fred, there's a potentially related question in the chat from Todd, excuse me. By laptop, do you mean through a cloud service or literally manageable to execute on a laptop?
It would run on a laptop. You'd have to have the MPI libraries installed and possibly a few others, but it should run, or you could run it in a Docker container that is appropriately configured.
Another one from the chat, does the National Water Model have or plan to have surface watersheds over groundwater potentiometric surfaces?
The current that's not in the development plans for version 2.1, which will become operational soon. It has been considered for version 3.0, but I don't remember if that's making it in. Trey, do you know?
No, we won't be doing potentiometric surface modeling in version 3.0. That'll be something that we can look at deploying in next gen.
Yeah, that would be a high priority for getting into next gen early. I see Seaway. Hi, Seaway. You wrote a question. The spatial and time resolutions of the next generation model, that's up to the user, depending on what the spatial and time resolution of the model they want to test is. As I showed that figure, different model formulations that use different discretizations. Some could be lumped at the whole catchment scale. I should mention that in the National Water Model context for next gen, we're looking at catchments primarily in the 3 to 10 square kilometer watershed, 3 to 10 square kilometers size, as to represent the fundamental computational unit. How those are discretized, what the time step of the particular formulation is, that's up to the model. And here's Taher asking a question, is there plan to include urban components? Again, the framework's model agnostic. If someone has a model that they believe will work well in urban areas, they could adapt it to work in the framework.
One more via the chat. What is the relation between the National Water Model and NOAA's current river forecast system?
Trey, you want to take that one?
More than happy to. So the existing forecasting system is based off of a DeltFuze application. The National Water Model has been running alongside that system for the last 4.5 years, and we don't anticipate changing that. Our goal here is to give the River Forecasting Center forecasters enough tools in their toolbox to be able to better inform their forecast and to better support decision services with their local partners. So The next generation system will follow in the footsteps of the current national water model, in that it will be running 24/7 in operations. It will provide a short range forecast every hour out to 18 hours. It'll provide the medium range out to 10 days, 4 times a day. We will be doing ensembles in the new next gen version. Effectively, all the capability and the forecast fidelity that we publish now in the national water model, that will be replicated in the next gen system. And we hope that we're going to be able to accelerate the skill of that system a lot more quickly than we have been with updates to date. So the two systems will ultimately be complementary.
I see a question from Joe Kreiner, another alumni of the Summer Institute a couple years ago. He asks, is water chemistry eventually or already part of the agnostic modeling capacity? So yes, again, in our long range plans, we want to forecast things like water temperature, turbidity, and we anticipate that the framework will be useful for other agencies that have more water quality prediction needs. So it is really intended to be an extensible framework that couples the data modeling aspects with the computer science, with the hydro and enviro science, and it really represents an enabling technology. So I think it's important to point out that one of our requirements is we don't want to prevent anybody from doing anything. Of course, the framework will have to have checks in it, the ability to detect when people are trying to do things that are incompatible. And that again is kind of a challenge, because the limits of compatibility are a gray area. But I do think that there will be some onus put on the operator to not do something that doesn't make sense. And if you look at the literature, there's a lot of instances of people who have done some certain things that don't make sense, but that'll be up to the reviewers to detect when that ultimately happens. And there's another question. Chen Yang asks, is the DeltFuze in 2020 version or higher? Can public users access the DeltFuze standalone or online systems to obtain the forecasts and modeling results?
That's relating to the existing forecasting system. I do not know the answer to that question in terms of what's available outside. For us, it's not just Fuse. We do have a Fuse stable build that is part of our community hydrologic prediction service. That's the internal system. I know that those configurations are available, but I don't have very many details off the tip of my tongue for that. I would recommend reaching out to Deltaris or Deltaris USA with that question.
Any other questions from anyone? I have to say that I was on the board of Quasi when National Water Model was first discussed, and that was really envisioned to be a model that the research community could get behind. That's a different problem than a framework that the community contributes to and uses to test hypotheses, et cetera. I believe that, I hope that this will generate considerable excitement, and by AGU we can give some demos and really provide a lot of impetus for community engagement in furthering the system. If one of the points that we have told our river forecast centers is, if you know of a model that performs well in your neck of the woods or your forecast area, we can test it. if it performs well and it complies with the standards of our operational system, we could deploy it operationally. Now, our operational bar, our standards are very high. It has to be fast, it has to be reliable, and that it doesn't crash. It has to be robust and that it can handle NANs and its input data stream and all that good stuff. And we want it to be as accurate as possible. It might be that one model formulation isn't the best in the growing season and the non-growing season. It might be that operationally it makes sense to, when the leaves fall, to switch to a different formulation. This system will enable that. Tahir, hi, he asks a question, is there a plan to provide model output as a web service? We have a plan, we're developing a model as a service capability. Our original impetus to develop this is to give us an environment to regionally test different formulations. And that will be a web service, and the tools that we're developing for that similarly will exist on GitHub. So yes, it would be the answer to that. And I see Ehab says not a question, but a statement. This is an exciting approach and will encourage collaboration. Thanks, Ehab, I appreciate that. Any other questions, comments? I've got to say it's been really exciting to present this. I believe it represents a significant advance, and it hopefully will enable. I've developed a number of models. Every time I do, I've invented my own data model, my own data standards. If we can get out of that business, it will go a long ways towards promoting interoperability, exchangeability, and testability of our different models.
Fred, there was one more question come up in the chat. Are there install instructions forthcoming?
I don't think we're pre-beta. I mean, we're literally trying to get the pieces. We've identified the pieces where, we haven't finished designing this extended BMI standard. Scott Peckham, working with our team, is trying to identify what the best way to do the serialized state work is in the BMI framework. So when we get to a beta point, I think we can promise that by AGU will be our kind of internal deadline to have that information available.
Yeah, and on AGU, just a note, we have submitted a technical session on next generation water modeling. The co-conveners are myself, Pat Burke from the National Ocean Service, from the total water compound flooding side, as well as Jared from Kawazi, and David Lesmus from the USGS. The session hasn't been accepted. The deadline was just today, but we did submit one on this topic, and we hope that everybody keeps an eye out for it and that we continue this conversation into this year's AGU and beyond.
Yeah, and we've also proposed a town hall on next gen for AGU as well, and hopefully we'll be in person.
Let's hope.
Okay, well, lots of exciting things coming in the future. Thank you everyone for joining us for this webinar. Perfect timing as we close out the hour here. And we hopefully look forward to seeing you in person at AGU. But thank you for joining us today virtually. This webinar is being recorded and will be on the Quasi YouTube channel, just to say it one more time. But thank you very much. And thank you so much to Fred and Trey for sharing your expertise today and for a great presentation.
Thanks, Julia. Thanks for coming, everybody.